Welcome to Math331, Lecture 18, give or take a little bit. We're going to continue our stuff on code theory. And so the big thing we're leading up to is the Hamming codes. And one of the things I love most about this is that first, they look really bad in terms of just how inefficient they are. But as you go deeper and deeper and deeper, it turns out it's actually doing a pretty good job. This is similar to a problem we talked about very early in the semester, but have not really looked at much since, and it is related to operations research. It's the checkerboard problem, or the chess problem, where you're putting queens down on the board. Has anybody gone forward and done some coding for that? This is a truly ghastly program to write. In terms of just how many queens, if you have an n by n board and you put down n queens, how many pawns can you safely place? When you look at the small data is quite misleading. It's like 0, 0, 0, maybe like 1, then 3. Yes?
When you say coding it, do you mean like to brute force it?
Even if you don't brute force it, even if you code it intelligently and you say linear programming, it's still a pain to do. And it's still a pain to do efficiently and quickly. You brute force, it's trivial, but we don't have the computational power to implement the trivial. If you try to use something like linear programming, each square is either assigned a king or well, we'll do a digression on that right now. So chess problem. Maximize number of safe pawns if n queens on an n by n board. And so here's a very simple way to do it. So xij is 1 if there exists a queen at ij and 0 otherwise. And then the sum ij goes from 1 to n of xij equals so what would that sum be? It would just be n. So we want to set this up as a system of equations. And so xij, these are going to be binary indicator variables. They're really nice. It's 1 if the thing is happening, 0 if it's not. Now we want to know if we can place a pawn on a square. So if we want to be able to place a pawn at ij, what must be true? So I want to know, can I put a pawn here?
You get to know if there are any queens on the same row or column or
Okay.
diagonals.
So the diagonals is the harder one, right? So can put pawn at ij if the sum j goes from 1 to n of xij equals 0. Because that would mean we have no queen in the ith row. And the sum I goes from 1 to n of xij equals 0. And some, I'll call it dij for the diagonal of ij, of x dij equals 0. So this is a very simple condition to check. Now we want to somehow convert this to something for Pij. So let's let Pij be greater than or equal to the sum j goes from 1 to n of xij plus the sum I goes from 1 to n of xij plus the sum over the diagonal ij x diagonal ij. So if you think about this, if there's a queen, let's see. Oops, okay, so I'm sorry. I think I want this the other way. So if this is 0, okay, I'm trying to do this without using the if statement. So when you learn linear programming, you learn how to program if statements. And so basically, if this is positive, we want this to be 0. So what if we look at 1 minus this? So what's the maximum this could be? You could be well, we've got to be careful. Because we could count the same queen multiple times. So what we could do is we could do a better thing of just how many queens could possibly be attacking this. And so rather than doing it like this, we could just do maybe n minus the number of attacking spots and divide this by n.
Wait, aren't the rows, columns, diagonals disjoint though? So you wouldn't double count.
No, because you could have something at I and j. We could actually have a queen at the location I and j.
Yeah.
So, again, right now the idea is just roughly how would we get some kind of constraint like this. So rather than phrasing it all like this, we could look at the number of things that are attacking ij. And then we look at n minus that and then divide this by n. So if something is attacking, this will be less than 1. The only way that this will equal 1 is if nothing is attacking. So then we let Pij be less than equal to this. And then we want to maximize the sum of Pij. So if something is attacking, this is now less than 1, and that's going to force Pij to be 0. So each Pij isn't 0, 1. Each Pij is a binary indicator variable. Can we put a pond in? If this number is greater than 1, greater than or equal to 1, then there is a queen attacking that square. This whole fraction now is less than 1, and so since Pij has to be less than equal to that, that forces Pij to be 0. If nothing is attacking, then Pij could be either 0 or 1, but since we're trying to maximize the sum, if we could put a pond there, we will put a pond there. So this is actually not that bad of a constraint. And again, depending on how much time you want to spend coding, for each square ij, you can have a set of queens that attack it, and just put that in here. Or you can do some over the whole column, some over the whole. You've got to be a little bit careful if you do it crudely like that, because then this could actually exceed n. So you just have to be a little careful. So it's probably best to just look at all the attacking squares, and then you avoid the double counting. So you can set this up as a system of equations. The problem is the equations have only integer values for their variables, and that makes the subject very hard. If it's continuous, if it's real valued, it's no problem. But because it's integer valued, this is very similar to the traveling salesman problem. If any of you have seen stuff like this, this is just terrible to solve things like this efficiently. How many of you have seen the old riddles, so-and-so has some number of sheep, and if you look at the number mod 5, you get if you put them into blocks of 5, you have 1 left over. In blocks of 7, you have this many left over, and then you're supposed to figure out how many sheep they have. How many of you have seen problems like this? Let me quickly see if I can find it. So I'll see if I can quickly find this. It's very similar in that you have some number of sheep, and I'm telling you the remainder when you break them up into groups of 5 and 7 and 11, and then you want to figure out how many are left over. I mean, how many do you have initially? And so the key for this is that you have an integer number of sheep. So there's frequently more than one solution. But there will be a smallest solution, or maybe for some problems like this, there will only be one solution that's positive. And so you can use that to get extra information, but there really is a potential infinitude of solutions. The next solution might involve you having over 1 million sheep, which is not really going to be a realistic solution. So here, the fact that the variables are constrained to be 0, 1 makes this a painful problem to run. You can do it by brute force. You can enumerate every possible, how many boards do we have? If we don't use any symmetry, there's n squared squares. Each square could either have, well, we have to choose n things from n squared. So if you want, as a rough count, how many board configurations do we have if we don't use symmetry? So how many ways can we place the n queens on the board if we don't deal with symmetry?
N squared choose n?
Yeah. So it's n squared choose n. So to get a rough sense, this is n squared factorial over n squared factorial n squared minus, n factorial n squared minus n factorial. So this is n squared minus 1 all the way down to n squared minus n minus 1 divided by n factorial. When n is large, n squared minus n, it's still roughly of size n squared. So this is roughly n times n squared divided by n factorial. And I would have n squared to the n. Right, and I don't pull off the n, put the n there. Each of these terms is about of size n squared. So roughly it's of size n squared to the n divided by n factorial. So by Stirling's formula, this is roughly n to the 2n factorial over n factorial. Stirling says m factorial is about m to the m e to the minus m square root of 2 pi m. I'm not even going to worry about the square root of 2 pi m. Just trying to get a rough sense. So n to the 2n factorial.
Oh, it's not factorial.
Oh, there's no factorial there. Oh, okay, good. And that's not bad. So I'd have an n to the 2n from that, and then n below would be an n to the n, e to the minus n. I'm not going to worry about the square root of 2 pi. So the n, I'll be getting an n over e to the n. The number of possibilities, roughly, if I don't take into account symmetry. So you can see how quickly this is going to grow. You know, if you try to do a 100 by 100 board, it's not happening. But you want to be able to get a sense like this for problems like this. Do we have a hope of going far enough to see? No. We can't do it. All right, so this means we can't brute force it. What if we just randomly choose boards and then just do statistics? So what if we gather a lot of data by randomly simulating 1 trillion 100 by 100 boards? Do you think that will be a good predictor for what the true value is? Why not?
There's probably only one board that gives you the best value.
So this is the problem, is what if there's only one board that gives you the best value? Or what if there's a very small number of boards that give you the best value? Or what if the best value is such a delicate configuration that it's very unlikely you would get close to that? Because again, we're not asking about what's the average number of pawns that are safe. What is best possible? So when you do experiments like this, you can gain some confidence about maybe what the average value is. But there could be an extreme, very delicate position where everything is perfectly aligned. So my question for you to think about this chess problem. Amazingly, have I told you or have you figured out what the answer is in the limit? What percent of the board can be safely populated by pawns?
All of it?
Basically all of it. It's absolutely amazing. In the limit, almost every square is safe. When you look at the small values, it's extremely misleading. And the reason I'm talking about this is there was a request to talk about operations research and linear programming, but also this segues in beautifully to Hamming codes. When you look at the small Hamming codes, it looks like it's not going to be that great of an idea. But as you go further and further, you see it becomes more and more efficient. It's very similar here, that for small values, the efficiency sucks. Almost every square is a square of death for the pawns. But as the board gets larger and larger, well, this kind of makes sense. We only have n queens to put, and we should be able to overlap the queens. Does anybody have any thoughts as to what would be a good packing strategy for the queens?
Just put them all in a box in the corner.
Yeah, box them in a corner. And if you don't have enough for box, have a couple of leftover spots. Fill up as much of a box as you can and just have a little bit of remainder. So now as an exercise, see how well you do with that. And what you will see is that's a first order. In the limit, you get 100%. Which means you don't need to be more clever. Right? If all you want is what's going on in the limit, and you can prove, oh, in the limit I get 100%, great. What I could then do is I could say, okay, now let's make your life interesting. What's the fluctuations? What's the rate of convergence to 100%? Then the box might not be enough. All right. But so this was a little bit of an introduction to how you can convert problems to this language of linear programming. You have constraints that involve linear combinations of your variables, and then you have a function that you want to maximize or minimize. For us, we want to maximize the number of pawns. And everything here is linear. The difficulty for solving these is that everything has to be integer. What do you lose when you have integer valued things?
You lose like moving along the whatever, the gradient or whatever.
Yes. So what class? What class is gone?
Analysis.
Yeah. I would say a little bit more than analysis, though. I would use a specific word. You know this word at least from high school.
Calculus.
Calculus. Calculus is gone if we are dealing with discreteness.
Is the packing strategy any better if you do like some approximation of a circular surface?
So this is a really good idea. So if rather than putting in your queens into something like this, what if you did something a little bit larger like this?
Yeah.
I don't know. That's a great thing to check.
It's like I don't know if that would actually like increase the like amount of the diagonal.
Yeah. Yeah, I have no idea. That would be a terrific thing to check. My feeling is I like this a little bit more because this is going to, I think, cut down on the number of diagonals. But it's definitely a shape worth checking. Okay, let's do the first crypto problem, the polynomial coding. And then maybe we'll do a discreteness and talk about computer science and then lead up to Hamming on Wednesday. So just out of curiosity, how many people know why we count in decimal? Yeah, I was going to say, you can raise your hands to answer that one, right? We have 10 fingers. I was talking to somebody who took them a long time to realize that's why we like base 10, is we have 10 fingers. Does the universe care that we have 10 fingers? You can prove the universe doesn't care. I can't prove the universe doesn't care. I don't think it does. What base does the universe like?
2.
Base 2 for computers, on, off, yes, no, true, false. Red Sox, Yankees, nice binary splits.
1.
Oh, sorry, the Yankees are no longer playing, I forgot.
I think 4 for quantum.
I'm sorry?
Is it 4 for quantum?
Are you talking about dimensions or
Oh no.
base? See, we're talking about base.
Base 1?
Quantum
No.
computer is base 4 though?
Well, so base 4 is part of the base 2 family.
Oh.
So you have 2, 4, you also have 8 and 16. So 16 is hexadecimal. As an aside, I'll list this one because it is October. Does anybody know why the computer scientist confuses Halloween with Christmas?
Is that because of the hex code system, right?
Because Oct31 is the same as Dec25. So if you write this in base 8, this is 3 times 8 plus 1, also known as 25. For some things, the universe actually prefers base 3. For storage, base 3 is a little bit more efficient than base 2. And I will show you why with a great discrete problem. So let's first return to the coding. So we have a triple ABC from quadratic, f of x is ax squared plus bx plus c. And you want to pass information in such a way that any three know the triple ABC, no to no. So I think we used language of Williams has a nuclear program. We don't have a large arsenal, but we do have enough to keep Amherst in check. Any three Williams professors, tenured of course, have the ability to launch. And then you could generalize the problem and say, well, let's say you now need a tuple with 10 components, and the president knows enough so that she can launch by herself. Maybe the provost and one other professor can do it. Deans of the faculty need 2 professors to do it, all the way down to etc. So you could actually control how much information people get. We talked about how clearly you can't give anybody all of A, B, and C, because then they could launch by themselves. If somebody knows just A and B, well, somebody else must know C then, right? And then you would have 2 people who could launch. So you can't give somebody 2 of the 3. And if we have a lot of people, let's say we have 10 people, if people just get 1 piece of information, you'll have 2 people who get A. And then there will be no third person that will help. So it doesn't seem like it's possible to do this. So the solution is I can't be giving them A, B, or C. I have to give them something else. What information should I give my professors?
Can you give them like parts of each answer?
What do you mean by parts?
You have to give them identical packages, though, right?
You do not have to give them identical packages. So I like the idea. What do you mean by parts? Because then they would have to know what part it is.
That's true.
You can give them like A plus B.
All right, so now somebody knows A plus B. All right, what else would they know?
But how would they know it was plus though? That's like another
Can we
thing.
tell them that? Can we say, this is what you know, A plus B?
Sure, you can tell them you know what A plus B is, and you don't know what A and B are, but I'm giving you the sum.
Oh, okay.
You could tell them that.
I see.
But then how would they get this out? If they find somebody else who knows B plus C, they could subtract it, they could get A minus C. But it seems like you're going to have similar issues. So for all these problems, it comes down to looking at it the right way.
Like, do they all get different?
You can choose what information you give them.
Oh, okay.
You want to give information in such a way that no 2 people can launch the weapon, but any 3 can.
Is this kind of similar to what we were talking about earlier?
I hope so.
If you like tell them like the number is such that if you like modify X like
You could try to play games with modding, but I think you would run into trouble as well.
I see.
But it might be possible to make that work where different people know different mods.
Yeah.
And then maybe somehow they combine. And no 2 people would be able to combine. So you might be able to mask it that way. I'd love to see it, and if you can, that's worth a homework problem.
When we say that like no 2 people know or no 1 person can know, is it just saying that like within the constraints of like a reasonable amount of time, or is it just saying like that, or are we assuming like infinite computing power?
Well, we'll give us infinite computing power.
We can't. We assume we can't try like every real number.
Correct.
Oh,
It's funny.
So we don't have to give them A, B, or C. We just need to give them things so that they can then deduce A, B, and C.
You give them like F of 0 or something.
So the first person gets F of 1, the second person gets F of 2, the third person gets F of 3.
Wow.
You give them points on a polynomial. How many points determine a straight line? Unless you're in the business world, in which case 1 point and you just ask the boss, what do you want your prediction? But for most of us, 2 points determine a unique straight line. A parabola. How many points determine a parabola? You give me 3 points, and there's a unique parabola going through the 3 points. And so on, and so on, and so on. And so this leads now to Lagrange's interpolation result, where if I give you some points, can you determine what the parabola is, or what the quartic is, or whatever that goes through them? Yes.
You said no, two people know, right?
So any three know, but no two know.
But if you have 2 points.
So if I have 2 points, that doesn't uniquely determine a parabola. If I just have
But
these
it's
two.
a straight line. I'm saying specifically C is 0. Or sorry,
A is 0. So
yeah.
yes. So if it was a straight line, if it was just BC, then any two people would be able to do, but one person would not.
Oh, so is there a restriction that A, B, and C have to they all have to be greater than like 0?
Nope, they could be 0.
Oh.
It could be a degenerate parabola, which is a straight line.
Okay.
But if I give you just one, let's say we're in the case of just B and C. If I give you just 1 point, you don't know what line goes through it.
Great.
You have infinitely many lines that could go through it. So one person would not be able to determine the pair BC. But if you give them another point, the two of them could then get together and compute. So with 3 people, what kind of parabolas might you want to avoid?
Like even ones?
Symmetric ones, even ones. If I give you a polynomial that's maybe symmetric about the vertical axis, what I might notice is, hey, the two of us have these 2 points. Let's guess that this is the parabola. This actually occurs in modern cryptography with primes, as you want to stay away from certain special primes, which are a little bit easier to find than generic prime factors. So you just want to be aware of things like this. I would probably make sure not to choose something like that. So then the question becomes, if you know these points, how do you figure out the polynomial? Well, let's see. If I look at here's f of 1, right? And now I want to plug in something that will give me f of 1 when x equals 1 and is 0 everywhere else. So I could look at n minus 1, n minus 1 minus 1, all the way down to 2 minus 1 over x minus 1 n minus x. N minus 1 minus x, dot to dot, 2 minus x. So if I take x equals 1, this numerator is going to equal the denominator, and I just get back f of 1. And if I take x to be 2 or 3 or 4 or all the way up to n, this is going to be 0. So this is going to be a polynomial of degree n minus 1, and it's going to take on the value f of 1 at 1. And then I could similarly do, now if I wanted to be 2 at 2, I would just do the same thing now. I would just have n minus x down to 3 minus x, 1 minus x, over n minus 2, dot to dot, 3 minus 2, 1 minus 2. And now when I plug in x equals 2, this will all cancel. This will give the f of 2, and at 2 this would vanish. And then you can just add in f of 3 with its crap, all the way to f of n with its crap. And here's the explicit way to get the polynomial. So, not only is this an existence, we have a way to find the polynomial that works. It's constructive. All we have to do now is multiply these things out. Okay? So it's actually very easy to find the polynomial that goes through all of these. Okay, so any questions about this? So, again, like most things in the class, when you look at it the right way, the problem is trivial. It takes a flash of insight to look at the problem the right way. And this is why the class is structured the way it is. This is why I'm giving you minimal stuff to read before class. It's really about looking at things and going through the thought process. I have a huge strategic advantage in that I have taught this class before. But this is one of the reasons why I like doing digressions, because let's push it to something I haven't really thought about maybe. And just, how do you think about this? How do you get it? Well, we realize you can't be giving people A, B, or C. There's no way to pass on that information. Maybe there's a sheep trick problem with modding that we could maybe work out. But of course, A, B, and C don't even have to be integers. So it's possible, but seems hard. But if we then say, well, actually, we don't need to know what A, B, and C are. That doesn't have to be given to us. We just need to know how to determine them once we talk to the other people. So we're not doing these things in isolation. If you think of streaming video, right? I'm assuming by now everybody has watched some streaming video at some point. For those of you who are watching this class later, who aren't here today, hi. All right, great example. The way we transmit information is taking advantage of the fact that we have a powerful computer on both ends. You don't have to transmit each pixel. You can just transmit, here's the red function, and I'm going to send essentially like a generalization of the Fourier coefficients. Have we talked about this in class, transmitting? All right, let me just briefly mention this, and then we'll go back to discreteness. So when you send pixels, it's expensive because you have to send every little color possibility. So each one is going to be a red, green, blue, triple, that often from 0 to 255. So let's imagine we just have the red. And we're going to have some function. Let's call it alpha of x, y for red. And we'll have similarly a green function and a blue function. If you've seen Fourier series, what we could do is we could do a two-dimensional Fourier series expansion. And then just send a two-dimensional Taylor series expansion and send just the first few coefficients. And the idea is, hopefully, the first few coefficients will do such a great job determining the function that we don't really need to send that much information. Instead of using Taylor series, there are more efficient bases to use. And this is where you get to things called Fourier series or wavelets. These are really powerful ways of transmitting information where you don't have to send that many pieces of information. And so we can just send a few pieces of information and then we can reconstruct. So imagine you have, 1, 1, 1 half, 1 sixth, 1 24th, 1 120th. You are sent that and you're trying to construct a one-dimensional function. Well, we take these and we get, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial. If we're looking at just the interval 0, 1, how good of a job do you think this is going to do approximating the exponential function on the interval 0, 1?
Well,
how well? Quantify. Where's the error going to be worse?
1.
Yeah. And at 1, the next term would be 1 over 6 factorial, 1 over 7 factorial. It's essentially 1 over 6 factorial. 6 factorial is 720. So you'd be off by essentially about 1 over 720. That's not bad. Yes?
How do you wrap each of the red, green, and blue values into functions to begin with? Like if you want to transmit them as, like an R of x, y?
Okay, so you would basically have the values of the functions here, correct? And then you would want to try to come up with some kind of function that would have those as its discrete possibilities. So you would want some kind of absolutely...
It's like approximation of
yeah.
the same thing?
Basically, I've now sampled a function, and I have these values. Frequently, what you do is you don't transmit, I believe, the actual values. You transmit the difference, I think, from one frame to the next. Because then the numbers are much, much smaller, much more clustered. A lot of them are hopefully going to be 0. How many of you have ever seen an old Disney film?
Oh, yeah, that too. I was going to say, are you a comp sci major? Did you ever take 134 with okay, I see. Because I think they do something like this. It's like data compression, like with Huffman encoding.
Right, yep. So I mean, there's lots of techniques. But what's nice is that can be done by your computer on the transmitting end, and then it can be uncompressed with your computer on the receiving end, so that the amount that you have to transmit is actually a small number of coefficients. So you're using the fact that you have strong, powerful computers on both ends. But okay, has anybody seen an old Disney movie or an old cartoon? What can you tell me about the animation that's done?
Like pixelated, and I feel like it's not as like smooth.
Well, frequently what you do is you actually have a static background, where the background is not changing, and there's maybe shadows coming from the main character, but that's it. The leaves are not rustling in the breeze. There's no great light reflection. And then you basically just have a fixed picture, and you have animation cells of Mickey Mouse or whatever walking down. So that really what's changing from frame to frame is that small amount. And you can control how much you need to do. So a lot of this stuff is all about what do we need to transmit. And so leading into the Hamming code, the idea is we want to transmit as much information as we can, as quickly as we can, while detecting and correcting errors. And so we talked about the tell me 3 times. You can do the tell me 5 times. You can do the tell me 7 times. And that's going to be very secure, and it's going to be very unlikely you will make a mistake if it's tell me 7 times. But only 1/7 of your message will be content. And so this is very similar to the checkerboard problem. The 3-1 code, the tell me 3 times, can actually be viewed as the first example of a Hamming code. And it sucks. It's less than 50% efficiency. But as the code gets more complex, you can get to the point where a majority to almost 100% of your message is actually content and data. And very little is redundancy. So with the checkerboard, it had to do with n squared versus n. N squared grows so much faster than n that eventually it doesn't matter what constants you have, n squared wins. For the Hamming codes, it's 2 to the n versus n. And while n could be competitive with 2 to the n for a while, eventually 2 to the n is going to destroy it. All right. So I'm going to leave you with a problem to think about for Wednesday's class. So here's the discrete version. You have a number like 100, and you want to write it as a sum of numbers. And we want each xi to be an integer. And you want to maximize the product. I claim as stated that this problem sucks. Why is this a bad problem to give you? How large can you make the product with these constraints?
100 to the n.
Why 100 to the n?
Well, the most any of them can be is 100.
Why? I'm sorry, I'm not seeing that.
Oh, they can be negative.
They can be negative. So give me a series of x's that will sum to 100 and will make this product as large as you want.
100, negative 100. 100.
Wait, can't you just take values of negative much greater?
Yep. All right, so right now your sum is 0.
Can you just do like 10 to the 20 and then 10 to the 20 or negative 10 to
Yeah, 10 to the 20.
100?
Let's do 10 to the m, 10 to the m, negative 10 to the m, negative 10 to the m, 100. Or if you have to have a couple more digits, you could do, 100 minus 1, 2, 3, 4, maybe 95, and then 1, 1, and a bunch of 1s. And if you do something like this, you can make your product astronomically large. So I clearly do not want to just say the x's must be integers. What should I say for the x's?
Positive.
Positive integers. Does it have to be positive integers? Could I allow some of the x's to be 0? Yeah, it'd be foolish, right? I'm going to try to maximize the product. I'm not going to have any of them be 0. But it might be convenient sometimes to allow yourself to have zeros just because of what you want to look at. Do you want to be looking at from 1 onward, or do you want to look from 0 onward? Now the problem becomes more interesting. Now we actually have a theoretical maximum. We can't do better than 100 to the n now. And in fact, I don't think we can reach 100 to the n. Unless, of course, n equals 1, which is not really that hard. But notice, n is free. I'm not telling you what's the best value of n to use. So you have freedom in choosing n. So the first question I want you to think about for Wednesday is, what is the maximum product, and how should you do it for the x's? So play with a couple of things. Try some different strategies. The next thing is, let's get rid of the word integer. Let's just say the x's are positive.
You can like.
So think about it. All right. So now if we just say the x's are positive, what's the best? And what I like about this problem is it goes from a discrete optimization to a continuous optimization. Now, there is something that is still going to have to be discrete in the continuous optimization. What's the one thing that still has to stay discrete and integer valued? N, right? I am not going to allow you to use 3 2/3 summons. Okay? You have to keep n as an integer. But the xi's do not have to be integer anymore. What's the best way to do this? This has applications in computer science. This is not just a problem because we need something to talk about. It is about what base is the best to store from. I think I've already given you some hints as to what number is circling. Does anybody remember what number is circling in the background?
3.
3 is circling. What other numbers are circling? 2.
16.
No, 16 is not circling. And there's another number circling between 2 and 3.
2.7.
No, okay, 2.7,
E.
yeah. And E is circling in the background. And the fact that E is closer to 3 is actually going to come into play in this problem. So this is one of my favorite problems. It can be solved using Calc 1 knowledge just barely. You essentially have to throw almost every idea you have in calculus to attack this one, which I love. And it's a great way to review some of the things that you might have thought were useless in Calc 1. But one of the real issues is, how do you pass from a real maxima to an integer maxima? How do you deal with the discreteness? There's a very famous problem called the Knapsack Problem. How many of you have heard of the Knapsack Problem? Do you remember the numbers? If not, I will have to quickly look it up.
What's the problem?
So you have a knapsack, and you want to fill the knapsack up with stuff to sell. And you want to have it as profitable as possible.
I thought there were no specific numbers. You like specify the weights.
Right.
And then the amount of money you get from each item and the capacity of the bag.
Right. And so the point of the knapsack problem is that the integer maxima can be very far away from the real maxima. So maybe you could hold 100 kilograms. And you have 3 items. The first one is 51 kilograms. And the next one is, the next 2 are 50, I believe. And the first one gives you $150 per unit. The next one is 100. And the next one is 99. And you can take any amount you want, and you just want to fill up your knapsack to do the best possible. Right? Of these 3 items, which item do you definitely not want?
The 99.
The 99. It's the same weight as the second, but a lower cost. So clearly you don't want this. Do we all agree just take item 1 and just fill up your bag with item 1? So if you can take a continuous amount, you would take 100 divided by 51 of that. So in the continuous case, you You take all of this. In the discrete case, what would you do?
Yeah.
All 2. You are not allowed to chop up a product. I will risk another Seinfeld reference. Who are my Seinfeld people who have any experience with Seinfeld?
When I was little.
All right. So Jerry Seinfeld has a terrible neighbor, Kramer, who's always basically causing issues. And at one point, Jerry is tired of him taking stuff from his refrigerator. So Kramer says, fine, I'll pay for my stuff. And so later in the episode, he opens up a can of Coke, takes a sip, puts it back, and gives like Jerry a couple of dimes.
Wow.
What are you doing? Well, I don't want the whole can. I'm just paying for the pot I drank. You can't buy part of a can of Coke. That sound is the sound of you buying the entire can. You can't just partly. There's a lot of things in life you cannot just take part of. So for something like this, you got to be all of item 2. Notice that the discrete maxima is nowhere near the continuous maxima. And since we spent some time earlier about the linear programming and the checkerboard problem, or chessboard problem, it's worth seeing something like this. This is the simplest example I know of just how painful the subject is. What you would love to do is say, look, find the real maxima and then just look nearby. This is not nearby. And this problem explains why it is such a difficult subject to find integer optimization. But there may be a situation where the integer maxima is near the continuous maxima if you have additional properties. And then life is good. And then you can find the integer maxima. Can anybody give me an example of a function where its maximum value at an integer is going to be close to its maximum value at a real?
A line.
A line, okay.
A parabola with its maximum.
Yeah. So if I give you a parabola like this, it goes up and then goes down. So you can find the real maxima here, and then just find and compare the 2 integers on both sides. So in a situation like this, you actually can go from the real maxima to the integer maxima. So again, there's a lot of really good techniques in what we're doing. This is stuff that solves real-world problems. This is not just problem solving to solve stuff on math competitions. This is e-commerce. This is modern encryption.